We now have the language that allows us to describe the objects that we are going to count. Sequences, collections, sharings, compositions, permutations, sets. But how to count them? Well, we will refer to two precise basic principles of counting. The first one is the so-called multiplication principle. It can be applied when the elements of a set X can be obtained through a sequence of steps, let us say k steps. We assume that at the first step we have a certain amount of partial outcomes, let us call it M1 possibilities for the first outcome. For each of these outcomes, assume that at the second step there is a fixed amount of possible outcomes, let us call it M2. And this for every step, up to the last one. But also, we require that from the element of X that is obtained in this way, we can uniquely determine the partial outcomes of step 1, step 2, step k. Equivalently, we require that different paths give different final outcomes. Well, if these assumptions are satisfied, then X has a number of elements equal to the product of the numbers M1, M2, Mk. It is very important to check the fact that from the final outcome, so you look at the final outcome, that is the element of the set X, that you can say exactly what happened at step 1, step 2, step k. Forgetting this condition is the first source of errors in combinatorics, and we'll see soon some examples. Let us prove the multiplication principle in the case of two steps. Well, the fact that from the final outcome of X we can uniquely recover the partial outcomes of steps 1 and 2 implies that there is a one-to-one correspondence between X and the pairs x1, x2, where x1 is an outcome of step 1 and correspondingly to x1, x2 is an outcome of step 2. Let us describe the possible pairs that we can obtain in such a way. Well, let us call A1, AM1 the outcomes of step 1. If we choose A1, we have M2 possible outcomes for the step 2. And the same for A2, A3, and AM1. Globally, we have M1 times M2, because M2 plus M2 M1 times M2 possible outcomes. So, M1 times M2 elements of the set X. As an application of the multiplication principle, it turns out that the number of elements of the Cartesian product of k sets, of k finite sets, is the product of their elements. Let's see why. Well, we can write the elements of the Cartesian product as a sequence, x1, xk, and form the sequence in k steps. In the first, we choose x1, the first element of the sequence. We have as many choices as are the elements of x1, and so on up to step k, where we choose xk, and we have as many choices as are the elements of xk. Notice also that from the final outcome, which is a sequence, x1 in the first term, so x1 in the first step. x2 is the second term, so x2 is the outcome of the second step. And xk is the last term, so it is the outcome of step k. So we can apply the multiplication principle, which gives the result. As an example, let us count the number of ways in which we can choose a president and a vice president from a group of 15 people. Well, we can do it in 2 steps. In the first step, we choose the president. We have 15 choices. And in the second, we choose the vice president. Also, from the final outcome, president, vice president, we know who was chosen at step 1, the president, and who was chosen at step 2, the vice president. And so we can apply the multiplication principle, and this gives us 15 times 14 possible choices. Now, let us warn you that a bad use of the multiplication principle is the first source of error in combinatorics. Often, if you don't check the fact that from the final outcome you can recover uniquely the partial outcomes, well, you may count more elements than what are the elements of the set that you are considering. Let us look at the following example. We want to choose 2 people from 3 in a group of 3 people. Well, clearly, we have 3 possible sets of 2 elements among 3. If people are named A, B, C, we have AB, BC, or AC. If we do it in 2 steps and we choose a first element of the committee of 2 people, we have 3 choices for the first person, and once we have chosen the first person, we have 2 choices for the second. So if we apply the multiplication principle, we get 6 possibilities instead of 3. Why? Well, the fact is that from the final outcome, which is a set of 2 people, we cannot say who was chosen in the first step and who was chosen in the second step. And so the multiplication principle cannot be applied in this situation. Let's see another example of a bad use of the multiplication principle. We have 3 people, 2 women and 1 man, and we want to form a committee with 2 people, one of which is a woman. So let us call W1, W2 the 2 women, and M the man. Clearly, we have 3 possible choices, W1, W2, W1M, and W2M. Actually, every set with 2 people contains 1 woman. Imagine we want to form the committee with the multiplication principle in 2 steps. First, we choose a woman among the 2, so we have 2 choices, and then we choose the other person. We have 2 choices. So if one applies the multiplication principle, we get 4 possible choices. But actually, there are no 4 groups of 2 people among 3 people. So why we get 4 instead of 3? Well, from the final outcome, we cannot say what happened in the first step or in the second step. For instance, consider the set of the 2 women. Who was chosen in the first step? And who was chosen in the second step?